Welcome to geometric sequence. So similar to our last video, a geometric sequence or a geometric progression, so a GP in this case, is a sequence in which the ratio between successive terms is constant. So we're now looking at a ratio, so we can get a ratio from a fraction. So have a look at these three examples. The first one is 2, 4, 8, 16, 32. So the ratio or the multiple between them is 2. So you're multiplying by 2 as you go up. For the second one, 20, 10, 5, 2.5, 1.25, your multiple or your ratio is a half. So you're multiplying by a half to get the next term. And for the third one, 3 minus 9, 27 minus 81, 243, the ratio is minus 3. So you're multiplying by minus 3 to get each successive term. So the ratio between terms, if you're unable to see it, is term 2 divided by term 1, and that has to equal to term 3 over term 2. So the ratio is T2 over T1 equals T3 over T2, or Tn, so the nth term divided by the term that's before it, T of n minus 1. Okay, determining the following sequences are GPs or not. So we're just going to put them into our ratio formula. So the second term divided by the first has to equal to the third divided by the second, has to equal to the fourth divided by the third. So for the first one, 30 over 10 equals 3, 90 over 30 equals 3, 270 over 90 equals 3. So the ratio is 3, so the sequence is a GP. For this one, 150 over 300 is a half, 30 over 150 is a fifth, 15 over 30 is a half. So since they're all not the same, the ratios aren't the same, it's not a GP. So the following numbers form a GP, find the value of x. So we'll use our formula. So the ratio is term 2 over term 1 equals term 3 over term 2. So x over 2 equals 72 over x. If you multiply this out, getting a common denominator, you get x squared equals 144. Now, hopefully you know that this is going to give you two solutions. One solution is plus 12, the other solution is minus 12. So that means we have two sequences that are possible. 2, 12, 72, which is multiplying by 6, or 2 minus 12, 72, which is multiplying by minus 6. So the formula for the nth term of a GP, and this once again is on your formula sheet, if we let the first term be A and the common ratio is R, then our sequence would be A for our first term, multiplying by R gets you AR, multiplying by R gets you AR squared, multiplying by R gets you AR cubed. So the fourth term is AR cubed, or the nth term is AR to the n minus 1. So now let's use our formula, Tn equals AR to the n minus 1. So we're going to find a formula for the nth term, and we're going to see how many terms are in the sequence. So here's our formula, Tn equals AR to the n minus 1. So the A is 10, the R is 3, so it's 10 lots of 3 to the n minus 1. Please be careful, this is not 30 to the n minus 1. Only the 3 is raised to the n minus 1. So how many terms are in the sequence? Okay, so we let the 590,490, that's our nth term. We let that equal to 10 lots of 3 to the n minus 1. Divide by the 10, because it's not attached to the power, so you can divide by the 10. And I'm going to show you two ways to get this. So the first way is we just guess what 59,049 is. It's 3 to the power of something, and that happens to be 3 to the power of 10. So therefore, since your bases are the same, you let n minus 1 equal to 10, so n equals 11. Hopefully you understand that because we've got a base, we don't have to guess, and hopefully you remembered that we could have used logarithms. So in using logarithms, since the base is 3, then the left-hand side becomes log base 3 of 59,049 equals the n minus 1. If you put that on your calculator, the log base 3, you get 10, add the 1, you get 11. So there are 11 terms in the sequence. Thank you.